So we're going to look at section 2.2, which is the properties of water. And as you go through this section, keep in mind that it's going to talk a lot about water and how the unique properties of water essentially allows life to exist here on Earth. So to start off, let's go back to covalent bonding, which we already talked about. Remember, covalent bonding is the type of bonding where they're cooperative or they share the electron. So you have polar covalent bond. You're going to notice throughout these slides that I don't necessarily put everything on the slide you're going to see. So it's going to force you to essentially take notes still on the lecture. But the cool thing with these screencasts is you can go back and replay any section that you want. So on to polar covalent bonds, which you can see right here. Basically, the definition for those are unequal sharing of electrons. And we're going to talk about what that necessarily means. But a great example of a molecule with polar covalent bonds is water. Now the question I pose to you is, why is water considered polar? And for anything to be considered polar or polar covalent, it has to have a region that is slightly positive and a region that is slightly negative. So when you look at an H2O molecule, you're going to see that the hydrogen atoms are both slightly positive and the oxygen atom is slightly negative. That's what makes water polar. So now we're going to talk about how life depends on a different type of bond called the hydrogen bonds in water. Now these bonds are the weakest bonds that we're going to discuss. So here is a picture of that wonderful hydrogen, water molecule. And you're going to see that the polar molecules have a slightly charged region. So as you can see, the positive and the negative. Non-polar molecules do not have charged regions. And then the hydrogen bonds form slightly between hydrogen atoms and any type of slightly negative atom. So right between the positive, so the hydrogen's positive, this is a hydrogen bond because it's a hydrogen bonding to a slightly negative atom. So more about hydrogen bonds. They're responsible for three very important properties of water that we are going to break down. They have a high specific heat, which is also referred to as a high heat capacity. They're responsible for cohesion. And they are responsible for adhesion. And we're going to go into what each one of these vocab words actually means. So let's talk a little bit about cohesion, adhesion, and surface tension. Cohesion is defined as water that is attracted to other water molecules because of polar properties. And we already talked about the polar properties being the slightly negative region and the slightly positive region. Adhesion is known or defined as waters attracted to other materials. And then the last definition I have down here is surface tension. And basically surface tension is when water is pulled together, creating the smallest surface area possible. We're going to go into these a little bit more. But for now we're going to talk about what's known as capillary action. Because water has both adhesive and cohesive properties, capillary action is present. So here's the definition of capillary action. Water's adhesive properties in the cause of capillary action. Water is attracted to some other material, and then through cohesion, other water molecules move to as a result of the original adhesion. So here's an example of capillary action. Think of water in a straw. When you suck up the water from a straw or a drink, the water's going to have to come together. It's going to have cohesion. and then it's going to come up through the straw. And basically, for those who are more into environmental science, that's why I have this picture of trees, is the way that water moves through trees is through capillary action. So that's when, again, the water's adhesive properties, allowing it to be attracted to some other material through cohesion. And remember, cohesion is when water is attracted to other water molecules. So they all the water comes together and then will move forward. So again, with the straw, the example I gave you guys with the straw is when you suck water up through a straw, the water has to come together to go up the straw. It's not like when you suck on a straw, the entire cup of water rises and comes to your face. It only comes through the straw. So high heat capacity. In order to raise the temperature of water, the average molecular speed has to increase. So it takes much more energy to raise the temperature of water compared to other solvents because hydrogen bonds hold water molecules together. Therefore, water has a high heat capacity. Think about it. How long does it take for water to boil? There's a reason why, for those who cook, they will pour some salt into the water because that will lower the boiling temperature. So back to the high heat capacity. The specific heat is the amount of heat per unit mass required to raise the temperature by 1 degree Celsius. So then we're going to talk about a couple of compounds that dissolve in water. A solution. So here's the definition. A solution is formed when one substance dissolves in another. A solution is a homogeneous mixture. What does that mean? Think about it. Homogeneous means it's the same. Solvents dissolve other solvents. And solutes dissolve in a solvent. Here's a picture. You have the solvent and the solute. So a couple over there, here's a definition for you guys. Water is a solvent of life. Again, a solute is a substance that is dissolved in a solvent to form a solution. I know that's a lot of S's. A solvent is a fluid that dissolves the solute. So here's an example. You have iced tea. Water is a solvent. Tea and sugar are the solutes because those are what dissolve in the solvent. So when Maddie walks into class with her coffee, her iced coffee is the solvent, and then her extra cream and sugar would be the solute. So a good thing to remember is like dissolves like. Polar solvents dissolve other polar solvents. Again, like dissolves like. Nonpolar solvents dissolve nonpolar solutes. And then keep in mind, polar substances and nonpolar substances generally remain separate. They're not going to dissolve each other. You mix a polar substance with a nonpolar substance, they will stay separate. Can anybody think of an example? Think about oil and water. Pour both of those in a cup and see what happens. So, there are some compounds that form acids or bases. So an acid, it releases a hydrogen ion when it dissolves in water. There's a high hydrogen ion concentration. Then there is a pH less than 7. So the more hydrogen, the lower the pH. So typically, looking at this picture, your stomach acid is around a 2. And the lower you go on the pH scale, which ranges from 0 up to 14, the lower numbers are more acidic. And as you can see down here towards the bottom, the concentration of hydrogen ions varies depending on how acidic or basic a solution is. So in terms of basic or bases, a base removes hydrogen ions from a solution. Therefore, there's a lower hydrogen ion concentration, and the pH tends to be greater than 7. So here's our picture. So the higher you go in the numbers, the more basic the pH level will be. So, and then to keep in mind, a neutral solution, anything when you consider it neutral, will have a pH of 7, which is right smack dab in the middle. So now we're going to talk about strength compared using the pH scale. Again, you're going to range from 0 to 14, and it's on a logarithmic scale, which means it gets 10 times bigger or smaller. So again, acids donate hydrogen ions when added to an aqueous solution and typically range from pH 0 to 6.9, and bases breaks up into hydrogen oxide ions and another compound when placed in an aqueous solution. And it ranges typically from 7.1 to 14. So distilled water typically has a pH of 7. So what does that mean to us? It's also considered neutral. Why? Write that down in your notebook. Why you think distilled water has a pH of 7 or is considered neutral. So here's a glorious picture of our beautiful pH scale. And again, it gives you kind of down the right hand side, it's going to give you what things are considered, on a pH scale of 2 versus grapefruit juice, which is a 3, all the way up to an oven cleaner, which is 13.5. You have seawater, bleach, and then over here you just see where the hydrogen ions are in terms of an acidic versus a basic. So a buffer. A buffer is a compound used to maintain a constant pH within a system. Also, to go back real quick to this slides, we talked about aqueous solution. I just want to let you guys know that to define an aqueous solution, it's basically a solution in which the solvent is water. So when we talk about an aqueous solution, it's when the solvent is water. Okay, going back to the buffer. Here's the example of carbonic acid yielding to bicarbonate ion. You guys should have spoke about this in chemistry. Real quick on the density end. Water is less dense than a solid. Should not be a shocker. You should know this. It's definitely less dense. This is because the hydrogen bonds are stable in ice. Each molecule of water is bound to 4 of its neighbors. So when the water is solid, water molecules are bonded together and the space between is fixed. It cannot move. An ice cube cannot be formed into anything else besides what it was frozen as, which is typically a square. When water is a liquid form, water molecules are constantly bonding and rebonding, and space is always changing. They're moving around. That's why liquids tend to fill the container they're poured into. So in review, you need to be able to name all the properties of water and understand what these properties mean. Adhesion, cohesion, capillary action, high surface tension, holds heat to regulate temperature, also known as high heat capacity, and less dense as a solid than as a liquid. And that is chapter 2.2. Again, rewatch this, watch it as many times as you need to, take notes, and bring questions to class.